Okay, think about some of the really iconic tech from maybe your childhood or perhaps even your classroom today. You know, the original Nintendo Game Boy, maybe a Sinclair ZX Spectrum if you're in the UK, the Sega Master System, or even like a Texas Instruments graphing calculator. What could these really different machines possibly have in common? Well, the surprising answer is a tiny, often unsung hero, the Z80 microprocessor.
That's right, an 8-bit CPU, first introduced way, way back in 1976. And what's truly mind-boggling is that its original 5-volt version, the classic one, only just got officially discontinued, like June 2024. That's nearly 50 years in continuous production.
Right.
Almost unheard of.
Incredible. So our mission for this deep dive is pretty straightforward. We're going to dig into the source material you've given us, pull out the most important insights, and basically give you a shortcut to understanding just how monumental and enduring the Z80's impact really was.
It really is an amazing story. So today, we're going to peel back the layers. We'll uncover the fascinating history behind this chip. We'll look at how its brilliant creators first envisioned it, the really clever and sometimes, frankly, shocking design choices that made it so powerful. And that includes the big reveal we hinted at, this quote-unquote 8-bit chip. It actually used a 4-bit arithmetic logic unit. We'll definitely get into that. Plus, its surprising reach. I mean, it ended up in places you just never expect.
Okay, let's unpack this. So the story really begins, maybe surprisingly, not with the Z80 itself, but with an Italian engineer named Federico Faggin, a truly pivotal figure in the early days of microprocessors. He was doing some really groundbreaking work over at Fairchild Semiconductor. He actually led the team that developed the self-aligned silicon gate transistor. Now, this method was so foundational, it's literally what gave Silicon Valley its name. But his bosses at Fairchild, they were, well, frustratingly slow to adopt his own innovations.
Yeah, and that lack of recognition, that slowness, it basically pushed Faggin to look elsewhere. He ended up joining Intel, which back then was, a pretty scrappy startup, formed by former Fairchild guys Gordon Moore and Robert Noyce. And these guys were different. They were absolutely ready to jump on new silicon technology. They saw the potential. It was the perfect spot for someone like Faggin.
But his first days at Intel sound like a real trial by fire. He gets handed this high-stakes Busicom calculator project immediately, and it's already massively behind schedule. Then, literally the next day, this engineer from Busicom, Masatoshi Shima, arrives from Japan. And he is, understandably, furious about the delays. So Faggin, 2 days into the new job, basically confronts him. There's this famous quote. Apparently, he told Shima to stop bitching and help me.
Wow. Yeah, that's pretty bold, especially given the, cultural context back then. But the amazing part is, Shima, after the initial shock, actually agreed. He stayed to help. And Faggin was apparently blown away because Shima turned out to be exceptionally talented at logic design. After just a quick intro to the methods, Shima basically single-handedly did the entire logic design for what became the Intel 4004, which many people consider the world's first true microprocessor. The first real computer brain on a chip. Just a huge achievement.
Okay, so let's fast forward a bit to 1974. Faggin's getting frustrated again, but this time with Intel's management. They saw microprocessors mainly as, like, a way to sell more memory chips, not as the main event. And this was despite his team constantly churning out better processors like the 808 and the really important 8080. He felt kind of stuck.
Right. And this led to what the sources call an enormous leap of faith.
Faggin decides to leave Intel, and he takes Ralph Ungerman with him. Ungerman was Intel's chief of microprocessor development. Big move, their goal. Start their own company focused only on microprocessors. And speaking of starting up, the name Zilog, apparently that has a bit of a story too.
Oh, totally. The story goes, Faggin and Ungerman spent several nights brainstorming, which apparently involved quite a bit of drinking trying to come up with a name. Zilog was the winner. Very Silicon Valley.
Love it. And then, almost by chance, at Intel's Halloween party in '74, Masatoshi Shima himself asks if he can join them. And just like that, the core team was complete. Faggin, Ungerman, and Shima.
An absolute dream team. But they picked a tough time to start. The mid-'70s economic backdrop was, well, rough. There was a severe global economic crisis kicked off by that devastating oil embargo in '73. Starting a new tech company then, it sounds, frankly, kind of bonkers. Absolutely bonkers. But news travels fast. Word got out about these Intel legends forming a new company. And it caught the attention of a really unexpected funding source. Exxon Enterprises. Yes, that Exxon, the oil company. They invested $500,000, which is roughly $3 million today. Now, why would an oil company do that? Well, they had a secret agenda. They wanted to rival IBM in the business computer market. Kind of weird, an oil company getting into tech, but that funding and that connection had a huge unintended consequence for Zilog later on. We'll get back to that.
Okay, so they have the team, they have the funding. What was Zilog's actual plan? How do you compete with Intel, especially when their 8080 chip was already doing pretty well?
Their mission was laser-focused.
Mhm.
Design a microprocessor that was flat-out superior to the Intel 8080. But, and this was crucial, make it fully software compatible with the 8080 and make it cheaper to produce. It was a classic embrace and extend strategy. Basically, offer Intel's customers an easy upgrade path, better performance, more features, but run all their existing software without changes.
And the Zilog team, it was small, right? But they worked incredibly hard. Faggin, even as CEO, was apparently hands-on with chip layouts. Shima handled the logic and circuit design. The sources say Shima could basically run the entire design in his head. There's even a story about him fixing a critical bug on the spot during a meeting just by thinking through it. Amazing. Ungermann focused on the tools, the simulators they needed, and the result was the Zilog Z80. So, what were the key things that made the Z80 better? What were those enhancements?
Well, first, that software compatibility was key. It ran all 78 of the 8080's instructions perfectly. But then they added over 80 new instructions. So the Z80 had about 158 total. This meant Z80 programs could just do more efficiently, offer with fewer lines of code. It also packed in way more registers, 14 compared to the 8087, including two brand new 16-bit index registers called IX and IY. Very useful. And get this, a duplicate set of the main general-purpose registers. This allowed for super-fast context switching, which was great for handling interrupts or multitasking, quickly swapping between tasks.
And the hardware side had some big improvements too, right? It wasn't just about software. I read about the built-in DRAM refresh circuitry. DRAM, that's dynamic RAM. It needs constant refreshing, right? Normally you needed another chip for that.
Exactly. By putting the refresh logic right onto the Z80 chip itself, Zilog eliminated the need for that external support chip. That might sound like a small detail, but for manufacturers building computers, it was huge. It simplified the board design, lowered the parts count, and cut costs, made the Z80 much more attractive.
Okay, what else?
It only needed a single standard plus 5-volt power supply. The 8080 needed multiple different voltages, which was kind of a pain. The Z80 also had its clock generation circuit built in, again, fewer external chips needed. And it had much more sophisticated interrupt handling with different modes you could choose from. So yeah, all these things together made it easier and cheaper for companies to design systems around the Z80, a really big competitive advantage over Intel at the time.
Now this brings us to something really fascinating you mentioned earlier. The ALU. Despite being sold as an 8-bit processor, doing 8-bit operations somehow. Its arithmetic logic unit, the core calculator part, was only 4 bits wide. How is that even possible?
Yeah, it sounds totally counterintuitive, right? It was a real shocker when reverse engineers discovered it years later, but it's a fantastic example of clever engineering within constraints. Here's how it worked. It performed 8-bit operations, like adding two 8-bit numbers, in two distinct steps, or cycles. First, it would operate on the lower 4 bits of the numbers. Then in the next step, it would operate on the upper 4 bits. And crucially, it passed the carry information if you need to carry the one from the low 4-bit operation to the high 4-bit operation. So the final 8-bit result was correct. It just took two internal steps using the 4-bit hardware.
Okay, so it wasn't magic, just clever decomposition of the problem. But why? Why do it that way?
It was all about saving space and transistors on the chip die. Remember, this was the mid-1970s. Chip manufacturing technology was still relatively primitive compared to today. Fitting everything onto the silicon was a huge challenge. By using a 4-bit ALU, they could significantly reduce the number of transistors needed for that core part of the processor. This allowed them to pack in all those other features we talked about, the extra registers, the DRAM refresh, etc., while keeping the chip size manageable and the manufacturing yield reasonable. The Z80 ended up with about 8,500 transistors compared to the 8080's roughly 6,000. That increase paid for the new features, and the 4-bit ALU helped make it possible.
So it was a deliberate trade-off, sacrificing a bit of internal simplicity for more external features and lower cost. And how did the actual computation circuit work?
The core circuit within that 4-bit ALU was designed to compute SUM, XOR, AND, or OR operations, depending on control signals fed into it. What's also really interesting is that for certain things, like calculating the parity flag, which indicates if there's an even or odd number of set bits, the Z80 used some really unusual, quite complex logic gate designs, things like pass transistor XOR gates, more complex than what competitors like the 6502 or even Intel's own updated 8085 were using. It just shows how Faggin and Shima were really pushing the boundaries of circuit design for the time.
Absolutely ingenious. And speaking of ingenious, Zilog had another trick up their sleeve, right? Something to stop others from just copying their design.
Oh, yeah. This was brilliant and maybe a little devious. Shema apparently embedded hidden traps into the Z80's layout. These were transistors that looked like they were part of the functional circuit if you just examined the chip layers visually. But they were actually connected directly to ground or in ways that would cause malfunctions. They were designed to be almost impossible to detect just by looking at a finished chip unless you knew exactly what the real circuit was supposed to be. So if someone tried to clone the Z80 by meticulously copying the layout.
Their cloned chip wouldn't work properly. It would have subtle or maybe even catastrophic failures.
Exactly.
Yeah.
These traps effectively acted like little time bombs for cloners. And they worked. They bought Zilog. Crucial time, the sources say maybe 9 months to a year before accurate working copies started appearing, particularly from Japanese competitors known for cloning back then. That head start was absolutely vital for Zilog to establish market share and ramp up their own production before the market got flooded with cheaper illicit copies. Really clever industrial sabotage baked right into the silicon.
Wow. Okay, so with the superior design, clever anti-cloning measures, and that attractive launch price of just $25, the Z80 took off.
It really did. It became one of the most popular CPUs worldwide pretty quickly by the late 1970s. Its first big wins were in that business and hobbyist microcomputer market. We're talking machines like the Tandy Radio Shack TRS-80 model, hugely popular. Also the Osborne 1, the first commercially successful portable computer, and the K-Pro 2. And these machines almost always ran the CP/M operating system. CP/M, Control Program for Microcomputers, was basically the standard OS before MS-DOS came along. The Z80 was the heart of that CP/M world.
And then it moved it to homes.
Massively.
Excellent.
Especially in the UK. It powered the Sinclair ZX series, the ZX80, ZX81, and the absolute legend, the ZX Spectrum. Huge cultural impact there. Also the Amstrad CPC and PCW computer lines, very successful. And in Japan, there was this thing called the MSX standard. It was an attempt to create a unified home computer platform, and guess what? It was entirely built around the Z80. Millions of MSX machines were sold.
And the gaming world. You mentioned the Game Boy earlier.
Oh, the gaming world absolutely loved the Z80. Countless arcade machines used it. Pac-Man is maybe the most famous example. Galaga, too. Galaga famously used 3 Z80s working together, a main CPU and 2 for sound and I/O, I think. Many, many Japanese arcade hits ran on Z80s. Then home consoles. The ColeDivision, Sega's Master System, and the Sega Game Gear handheld, all Z80 powered. And even when consoles went 16-bit, like the Sega Genesis or Mega Drive and the Neo Geo, they often kept a Z80 on board, usually to handle the sound processing. It just wouldn't go away. And yes, the Nintendo Game Boy. Its custom CPU, the Sharp LR35902, wasn't a pure Z80, but it was heavily derived from it, and the Intel 8080. So Z80 DNA ended up in the pockets of literally millions and millions of kids and adults worldwide.
That's incredible reach just in computing and gaming. But you said it went even further into less obvious places, embedded systems.
Absolutely. This is where its longevity really shines.
Mm-hmm.
You mentioned the Texas Instruments graphing calculators earlier, the TI-81, 82, 83, 84 series. For decades, students learning programming on these calculators were actually learning Z80 assembly language, even if the textbook didn't explicitly say so.
So I might have been a Z80 programmer without knowing it. What else?
Industrial control systems running factories, machinery, telecom equipment, think modems, early fax machines, office PBX systems, those internal phone networks, even satellite control systems, apparently, which is kind of mind-blowing for an 8-bit chip from 1976. Music synthesizers, too. The Sequential Circuits Prophet 5, a legendary synth and the first programmable one, used a Z80. The Roland Jupiter 8 They used it for scanning the keyboard, controlling the settings, and later handling MIDI communication, the standard for connecting electronic instruments.
MIDI, wow, and even more everyday items.
You bet. Things like smart light bulbs today might still use Z80 derivatives, thermostats, maybe your oven, network doorbells. And perhaps the most surprising one I read about, the internal controller logic inside some IDE chipsets that bridge to modern SATA drives in PCs. An 8-bit core managing data from multi-gigabyte drives just everywhere. And a key reason for this ubiquity was Zilog's strategy. They actively licensed the Z80 design to other manufacturers around the world, companies like Mostec, NEC, Sharp, Toshiba. This multi-sourcing assured customers of supply, drove down prices through competition, and really fueled its global adoption. It wasn't just a great chip, it was a great business strategy too.
Okay, as we wrap up, let's circle back to that what-if moment involving Exxon. You said their secret plan to rival IBM inadvertently hurt Zilog. How?
Yeah, this is the ironic twist. Exxon's ambition to take on IBM meant that when IBM was designing its revolutionary personal computer, the IBM PC, they were essentially forbidden by corporate politics, or at least heavily discouraged, from using technology sourced from a direct competitor like Exxon-owned Zilog. So even though the Z80 was arguably a very capable chip for the task, IBM couldn't really consider it seriously. This pushed them towards Intel and their new 16-bit processor, the 8086, and its cheaper sibling, the 8088. And that choice, as we all know, set the course for the entire future of personal computing. The IBM PC standard was built on Intel's x86 architecture, which dominates desktops and laptops to this day. Zilog, because of its owner's unrelated ambitions, missed out on potentially being the chip inside the IBM PC. A huge, history-altering missed opportunity.
Wow, talk about unintended consequences. And what happened within Zilog after that initial Z80 boom? Did they manage to follow it up successfully?
Not really, unfortunately. There were internal struggles. Conflicts reportedly arose between Faggin and Ungermann. Faggin eventually stepped down as CEO around 1980, and Exxon took full control. Zilog tried to follow up the Z80, but their main attempt, the 16-bit Z8000, made a crucial mistake. It wasn't backward compatible with Z80 software. This made it a much harder sell compared to chips like Motorola's 68000, which is technically very impressive and found huge success in machines like the Apple Macintosh, the Atari ST, and the Amiga. The Z8000 kind of floundered. Ironically, Zilog did develop Z80 successors that were backward compatible and quite capable chips like the Z800, also called the Z280, and later the much more modern EZ80 series. But Zilog's management at the time didn't seem to prioritize them, focusing instead on other ventures that didn't pan out. They kind of missed the boat on leveraging their own strongest asset, that massive Z80 software base.
So summing it all up, nearly 50 years of production for the original, descendants still being used today. Despite not winning the big PC war, the Z80's legacy seems immense.
Absolutely profound. It was undeniably a cornerstone of that whole 8-bit era, particularly for all those CP/M machines, which really laid the groundwork for personal computing software as we know it. It was a fantastic educational tool. Countless universities, technical schools, and hobbyists used Z80-based trainer kits like the microprocessor to learn the fundamentals of computer architecture and assembly language. It taught generations how computers really work at a low level. And its design philosophy, especially that initial backward compatibility with the 8080, set a really important precedent. That strategy of embracing and extending an existing standard was later perfected by Intel itself with the x86 architecture. Plus, today it's just beloved in the retro computing community. People are still designing new hardware for it, writing new software, keeping the spirit alive. It has a real cult following.
So here's a final thought for you to mull over. Despite never quite reaching the PC dominance that Intel achieved with x86, maybe because of that Exxon twist or those later strategic missteps, the Z80's incredible journey, nearly 5 decades long, its quiet presence in everything from Pac-Man to your graphing calculator, maybe even parts of your modern PC or smart home, it really shows that sometimes a single, exceptional, well-designed one-hit wonder, even if it doesn't conquer the mainstream, can have an utterly disproportionate and unbelievably lasting impact, quietly shaping the tech landscape we live in for generations.